Intermediate Algebra, Section 3.2. We're now going to look at a third method for solving a system of two equations known as the elimination method, which makes use of the addition principle. This is sometimes also known as the combination method. So let's take a look at this, how it works. The elimination method is basically the adding of the two equations together. So you want to make sure that your variables are lined up. And when you add them together, you want one of the variables to cancel out. And in this first example, when I add the x's, 1x plus another x makes 2x. Adding the y's, they do cancel out since they're additive inverses, is equal to 6. The result is one equation with one unknown, which allows us to solve for the variable. So dividing both sides by 2, we end up with x is equal to 3. These two equations of lines intersect, and the common x value is 3. All we need to now do is to solve for the y value that goes with that. So plugging x equal 3 into either one of the equations, say the first one, x, which we found to be 3, plus y is equal to 4. Subtracting 3 from each side leaves a y equal to 1. So the solution to this problem of these two linear equations is the common point 3, 1. Not all equations work out that way, so that when we solve this system that they automatically cancel out. So we have to use and maintain equality, multiplication property. And in this case, if this y, for example, was only a positive 2, we could add these two equations together. Well, no problem. If we multiply this by a negative 2, we'd have a negative times a negative, a positive 2y. So to do that, we just need to maintain equality by multiplying every term by that value. So the first equation, we are doing nothing to. The second equation is getting a tweaking of a multiple of negative 2. Negative 2 times 3x leaves negative 6x. A negative times a negative is a positive 2 times y. And a negative 2 times 7 is negative 14. Now when we add these equations together, 5x and negative 6x leaves a negative 1x. The y's do cancel out, and we end up with a negative 6. Multiplying or dividing both sides by negative 1 leaves us with x equal to 6. These two linear equations intersect when graphed in a common point of at least the x-coordinate of 6, plugging that into either one of the equations, and it doesn't matter which one we plug it into. If we plug it into, say, the second equation, we have 3 times x, which we found to be 6, minus y we're trying to solve is equal to 7. That leaves an 18 minus y is equal to 7. Subtracting an 18 from each side leaves negative y equal to negative 11. And dividing both sides or multiplying both sides by negative 1 leaves us with y equal to 11. So the point of intersection between these linear equations is the point 6, 11. It's always a good idea in math to check your solution. We can plug this into one of the equations, preferably that we haven't used, to verify that our solution is correct. Since we used the second one to find our second value, let's see if this is, in fact, a solution to the first equation. So 5 times x, which is 6, 5 times 6 would be 30. This is going to be our check. Y we found to be 11, so 2 times 11 would be 22, and 30 minus 22 is in fact 8. So we have proof that we have solved it correctly. In this next example, looking at this to find a common factor, you may be daunted by having this fraction, but no problem. we can eliminate any rational coefficient by multiplying by the least common denominator. We only have one denominator here, which is 4. So multiplying every term by 4 will eliminate the fraction. So I'll leave the first equation alone. Multiplying the second equation every term by 4, we have 4 times 5x is 20x. The 4 in the numerator cancels out the 4 in the denominator, leaving a negative 3y, and 4 times 7 is 28. Now we can play the game of what do we need to do to eliminate one of the variables. And here, if we look at the y's, their opposite sign, that's always a good start. And if this second one was only a 6, and to accomplish that, all we need to do is multiply by 2. But to maintain equality, every term needs to be multiplied by 2. So again, we are not doing anything to the first equation. And if we'd thought through this process, we could have combined these two steps and multiplied by 8. But just to illustrate here, step by step, how we're arriving at a setup so that we can use the elimination method, we'll break it down. So 2 times 20 leaves us with a 40x. 2 times negative 3y is a negative 6y. And 2 times 28 is 56. Now adding the two equations together, we end up with 44 x's. Combining the x's, y's are gone, and adding the constant terms leaves an 88. Solving for x, because we now have one equation with one unknown, we can solve for that variable, and we end up with x is equal to 2. So these two linear equations do intersect, have a common point. The x-coordinate has a value of 2. Plug that value into either one of the equations. If we plug it into the first one, 4 times x, which we know has a value of 2, plus 6y is equal to 32. 4 times 2 is 8. Subtracting an 8 from each side leaves us with a 6y is equal to 24. And dividing by 6, we end up with y is equal to a 4. So the common point or point of intersection between these two lines is the point 24. And again, it's always a good idea to plug that value in to verify that it does work. I should mention, before I go on, we were doing multiplication all along, but we also can maintain equality by dividing. And if you look at this original equation, each one of these terms had a common factor of 2. While I was multiplying everything by 4 to get rid of the fraction, could have divided every term in this first equation by 2, which would have left a 2x, a 3y, and a 16, which would have been ready to do the elimination method of adding those two equations together. Most of us think multiplication, but as long as we're maintaining equality, sometimes dividing to factor out and reduce the equation is a faster method and certainly an option. All right, back to this last problem. There are times when we need to manipulate both equations to get a common value so that when they're added together, they cancel out. And here's the case. I can't do anything with the 2 to get it to 5 easily, or the 3 to get it to be a 7 easily. So we're looking for the smallest number that you choose the variable. Let's pick on x, for example. The smallest number that 2 and 5 go into is 10. That would mean I need to multiply this first equation by 5 to bring this up to a 10. And this needs to be multiplied by a 2, but I want it to be an opposite. I don't want it to be a positive 10 so that we would end up with 20x. We want these to cancel out. So to anticipate that, multiply by a negative 2 instead. The result is 5 times 2x is 10x. 5 times 3 is 15y. And 17 times 5 gives us an 85. Multiplying every term by -2 gives us a -2x, a -14y, and a -58. Now add the two equations together. By design, the x's cancel out. 15y plus a -14y leaves a positive y, and 85 plus a -58, or just -58, leaves a 27. What we have are intersecting lines for this set of linear equations as well. We have our y coordinate. We can plug it into either one of the equations. I like smaller values, so let's do the first equation. 2 times x, which we don't know, plus 3 times y, we found to be 27, is equal to 17. Simplifying, 3 times 27 results in 81. And solving for the variable, we'll subtract an 81 from each side. That leaves a 2x is equal to a -64 when you take 17 minus 81. And last, divide both sides by 2, ends up with a -32. So pulling these two values together in an ordered pair, the common point of between the two equations, or the point of intersection, is the coordinate -32, 27 for the point.